In this lesson, we're going to introduce several reactions of aldehydes and ketones, focusing on acyl addition and acyl addition elimination. Aldehydes and ketones have two primary modes of reactivity, acyl addition and acyl addition elimination. All carbonyls are characteristically electrophilic. The carbonyl carbon is considerably electron deficient due to the two bonds to oxygen. This means that carbonyls react with nucleophiles. Acyl addition is the addition of a nucleophile across the carbonyl pi bond. In the generic example here, you can see the molecule NUH has been added across the pi bond. The reaction results in the formation of an alcohol. Acyl addition typically occurs when the nucleophilic atom is not an electronegative atom. This is the mode of reactivity seen with nucleophiles such as cyanide or organometallic reagents. The other major mode of reactivity for aldehydes and ketones is acyl addition elimination. This is simply an acyl addition followed by the elimination of water to create a new pi bond. The generic example shown here starts with the addition of NUH across the pi bond to form an alcohol. The alcohol is then protonated, enabling water to be expelled, forming a new pi bond. Acyl addition elimination is typically seen when the nucleophilic atom is an electronegative atom. So why does acyl addition occur when the nucleophilic atom is not electronegative, and acyl addition elimination occur when the nucleophilic atom is electronegative? Well, funnily enough, it has nothing to do with electronegativity. When you compare the two generic reactions shown here, you can see that the initially formed acyl addition product in the acyl addition elimination has a lone pair on the nucleophilic atom that's missing in the acyl addition. That lone pair is what's used to displace the water molecule after protonation of the alcohol in the acyl addition elimination. Without that lone pair on the nucleophilic atom, the displacement of water cannot occur, and so the reaction stops after acyl addition. Most electronegative atoms, like nitrogen and oxygen, will have a lone pair present on the atom when they're not charged. This means that nucleophiles such as alcohols and amines will induce acyl addition elimination. In contrast, elements that are not electronegative, like carbon, do not have a lone pair when electronically neutral. This means that nucleophiles such as cyanide and organometallics will result in acyl addition. Both aldehydes and ketones undergo the exact same acyl addition and acyl addition elimination reactions. Aldehydes are, however, almost always more reactive than ketones, and there are two primary reasons for this. Ketones have two carbon groups bound to the carbonyl. Aldehydes have one carbon group and a hydrogen. This means that aldehydes have less steric hindrance on the carbonyl carbon, allowing nucleophiles to more easily attack. The additional alkyl group of a ketone also stabilizes the partial positive charge present on the carbonyl carbon. Alkyl groups simply have more electron density than a hydrogen atom. That extra electron density can be pulled in to stabilize the partial positive charge on the carbonyl, making it less reactive. So in this lesson, we're going to focus on acyl addition, the reactions of aldehydes and ketones with nucleophiles that are not electronegative. The first reaction is cyanohydrin formation. Both aldehydes and ketones can react with hydrocyanic acid to form a cyanohydrin. As you can see in the example, the product has both nitrile and alcohol functional groups attached to the same carbon. Cyano is simply an older term for a nitrile, and hydrin an older term for an alcohol. The reaction requires hydrocyanic acid, an extremely dangerous, deadly gas. To make running the reaction safer, the hydrocyanic acid is typically generated in situ. One common way is to use an inexpensive cyanide salt like potassium cyanide under acidic conditions. If we look at the reaction mechanism, we see that it is a perfect example of acyl addition. In the first step, the nucleophilic cyanide attacks the electrophilic carbonyl carbon, breaking the carbon-oxygen pi bond and forming a new carbon-carbon bond. In the second step, the alkoxide intermediate is simply protonated to give the final alcohol product. The cyanohydrin reaction is actually reversible. Under basic conditions, the reverse mechanism occurs. A strong base would deprotonate the alcohol to form an alkoxide, which would then collapse to form the pi bond, expelling cyanide and reforming a carbonyl. This expulsion of cyanide actually explains why things like apple seeds, peach pits, and bitter almonds are toxic. The toxicity arises from mandellonitrile and mandellonitrile derivatives. Mandellonitrile is a naturally occurring cyanohydrin. Once ingested, these compounds can find their way into the bloodstream, and human blood has a slightly basic pH. The basic conditions break down the mandellonitrile, forming benzaldehyde and releasing toxic cyanide. The most common examples of acyl addition involve the reactions of aldehydes and ketones with organometallic reagents and hydride donors. Both aldehydes and ketones undergo acyl addition with classical organometallic reagents, organolithiums, Grignard reagents, and acetylide ions. These reactions are extremely useful synthetically because they result in the formation of a new carbon-carbon bond. In the first example, we see acetone reacting with ethyl lithium followed by an acidic workup. The reaction forms a new carbon-carbon bond, resulting in a tertiary alcohol. In the second example, we see a similar reaction of acetone with an acetylide ion. In each case, the reaction mechanism is identical to that of the cyanohydrin formation. The strongly nucleophilic organometallic reagent attacks the electrophilic carbon of the carbonyl, and the resulting alkoxide is protonated in the acidic workup. Aldehydes and ketones undergo a similar acyl addition reaction with hydride donors. Remember that hydride is H-, which really doesn't exist, but there are reagents that can act as hydride donors. While the reaction is a form of acyl addition, organic chemists typically refer to this as a reduction. In the first example, we see benzaldehyde reacting with sodium borohydride and methanol to give benzyl alcohol. Not surprisingly, sodium borohydride acts as a hydride donor. It contributes an H- to the carbonyl carbon, and the resulting alkoxide is protonated, in this case by the solvent molecule methanol. In the second example, we see the exact same transformation carried out with a different set of conditions. Here, lithium aluminum hydride is used. Lithium aluminum hydride is a considerably more powerful hydride donor compared to sodium borohydride. Because of this, lithium aluminum hydride is not compatible with any protic species. The reaction must be kept free of water or any other protic species until the addition of hydride is complete. Once the hydride has been transferred to the carbonyl, the reaction is worked up with a strong acid. Hydride donors are usually pretty easy to recognize. If you ever see a metal or metalloid with hydrogen atoms attached to it, it's probably going to act as a hydride donor. In sodium borohydride, we have boron, a metalloid, with 4 hydrogens attached. In lithium aluminum hydride, we have aluminum, again with 4 hydrogen atoms attached. We can predict that each compound should act as a hydride donor, an effective source of H-.